Balancing oxidation reduction reactions of an alkaline or basic solution. First, we have to break up our overall reaction into two half reactions, omitting H plus, OH minus, H2O, and making sure each half reaction has similar elements. Next, for each half reaction, we have to balance all the elements except for oxygen and hydrogen. As seen, Cr is balanced for both half reactions and Mn is balanced for both half reactions. Next, we have to balance for oxygen. For each half reaction, we balance the O's by adding H2O to the side of the reaction that is deficient in oxygen. Add one water molecule for every oxygen needed. We add 4 waters to the first half reaction. To our second half reaction, we will add 2 waters. Next, we have to balance for hydrogen. For each half reaction, we add H plus to the side of the reaction that is deficient in hydrogen. We add 1 H plus for every hydrogen needed. Since we have 8 hydrogen in the first half reaction, we add 8 H pluses. And in our second half reaction, we have 4 H pluses. Since this is a basic solution, for each half reaction, we add OH minus to both sides of the equation. We add enough OH minus to neutralize the H plus that we just added. So since we had 8 H pluses, we have to add 8 OH minuses to both sides. And for our second half reaction, we have 4 H pluses, so we have to add 4 OH minuses to both sides. Next, we combine to form water. Now you can take the H plus and OH and combine them to form water. In our first half reaction, we have 8 H2Os, which were combined. In our second half reaction, we have 4 H2Os. Now we have to cancel out any water molecules that appear on both sides of the reaction. In our first half reaction, we have 4 waters on one side and 8 on the other, which will reduce to 4 H2Os and give us a new half reaction. In our second half reaction, we have 2 H2Os and 4 H2Os, which will reduce down to 2 H2Os and give us a new half reaction. Next, we have to add in our electrons. To do this, we have to find out which half reaction lost electrons and which half reaction gained electrons, and how many electrons were transferred. For chromium 3+, the 3+ charge shows us that the oxidation number is +3. So for Cr042-, we have to find out the oxidation for the Cr. The Cr042- has a -2 charge, which gives us an overall -2 oxidation number. So Cr plus 4 oxygens equals -2. Since oxygen always has a -2 oxidation number, we see that Cr plus 4 of our -2 oxygens equals -2, giving our Cr a +6 charge. This means that chromium lost 3 electrons, and we show this in our product. In our second half reaction, MnO2 does not have a charge. Therefore, Mn plus 2 oxygens equals 0. Since oxygen is always a -2, Mn plus 2 -2 oxygens equals 0, giving Mn a +4 oxidation number. In the second part, Mn's charge is +2, giving it a +2 oxidation number. We see that it went from a +4 to a +2 oxidation number, meaning it gained 2 electrons. And we add this into our half reaction. Next, we have to multiply one or both half reactions by a whole number so that both half reactions have the same numbers of electrons. For the first half reaction, we must multiply by 2. And for the second half reaction, we must multiply by 3 in order to give us 6 electrons in both half reactions. When you multiply the first half reaction by 2, you should get 16 OH minus plus 2 Cr3 plus 2 CrO4 2 minus plus 8 H2Os plus 6 electrons. And for our second half reaction, we'll get 3 MnO2s plus 6 waters plus 6 electrons plus 3 Mn2 plus 12 OH minuses. Now we have to add the half reactions. Our electrons will cancel out, as will some of our H plus, OH minuses, and H2Os. As we can see, our 6 electrons cancel out, our waters cancel out and are reduced, and our OH minuses are canceled out and reduced. Now we can write out our new equation. And this is balancing oxidation reduction reactions of a basic or alkaline solution.